The title of my talk is Multi-Material Robotics, which I chose sort of for two reasons. It's really a very broad general title that you might say that could apply to anyone's talk on robotics. We don't all build things from a single material or a single chunk of metal or plastic. But the talk title I think was appropriate because it sort of defines two things. One is the only title that I think could encompass all of my work, which is a little bit diverse. So it's all encompassing in that regard. And then the second reason is it says a little bit about the methodology that I use in the design process for these robots. So they're very, I leverage the properties of the materials in the functions of these new robots that I'm aiming to use in novel applications. And by novelty, I mean applications where robots have had difficulty succeeding or have even not been capable of functioning well in these new environments using sort of traditional approaches to robotic design. So a lot of it is driven by the materials that I use and then the fabrication process, which goes hand in hand with that. So those are the two reasons I picked this very broad title to describe my work that hopefully you'll understand by the end of this presentation. So I'll start first by talking about the traditional sense of robotics that people know the field by. Robots have been around for a while now, you could say, but they came about through industrial applications. So this is a view of robots that are used on an assembly line for automotive manufacturing. They're used heavily for these types of tasks that would be difficult, dangerous, or just tiring for people to do alone. So obviously that increases our productivity in these industrial applications beyond the capacity or what we would like to assume is the cost for these types of products to be so widely available as they are. So they're very important in their role in industrial applications. So I wouldn't go so far to say as that this is an outdated form of or use of robotics. But I will say that there are applications beyond this that these types of robots wouldn't do well in. For instance, I wouldn't want to put one of these in my kitchen or my bedroom to help me with chores, to fold laundry or do dishes. And you can see from this picture alone, what's really common in these factory environments are these cages or walls that are put up around these robots, which are designed to function mostly independent of human intervention. And that's for these reasons that they're inherently not the safest machines to be working around, especially when they're pre-programmed to whip around heavy tooling or materials to very precise trajectories that, and to save costs and complexity, don't have a lot of feedback built into their programming. So there's not a lot they can do if you get in the way to try to not hurt you. So I started in this type of robotics during my undergraduate research experience. And so to the right are three pictures of shots of a gantry system that I designed for a similar process to this automotive manufacturing, but for airplanes. And so this was work sponsored by Boeing. And these gantry systems were towards automating aircraft assembly, which even to this day is primarily a manual task. So they don't have these assembly lines working at the same capacity for planes that they do for automobiles. And so that's what got me interested in robotics and started in the field, and particularly in my research, because I started this as an undergraduate research assistant. So I moved on from these applications in robotic automation to continue my graduate degree as a master's student at Michigan, working on a robotic tentacle type system, you could say. So the top picture here is a hyper-redundant robotic manipulator built for a mobile robotics application for manipulating objects on a mobile platform. And after that, for 4 years, I did, as was mentioned, work at a small startup company out of a lab at Michigan. The Human Biomechanics Control Lab spun off a company called Intelligent Prosthetic Systems. And the purpose of this company was to develop robotic prostheses or assistive devices, primarily for below-the-knee transtibial amputees. And so these two projects during my master's career and then the next couple of years after sort of started to shape my understanding of the traditional sense of robotics in terms of limitations, as well as new possibilities for the field. So the hyper-redundant robotic manipulator, the long tentacle arm, taught me a lot about practical limitations in these high-power systems. If you rely on conventional approaches using, this had an off-board motor powering the whole system, but on the distal links, this is only one module of many that would be strung together in sequence, was what amounted to a very heavy gearbox. And if you stick to those materials and design techniques, you end up with more or less an impractical system. To tell me sort of the limitations of using just those components in that approach. And then the work in the robotic prostheses gave me the first insight of my career into ways that these robots can be translated from their sort of fixed, isolated silo of applications in factory use to these more personalized applications. And so you can imagine how indispensable our phones are to us, how much this would mean to us to be carrying around this robotic device. It becomes a very personal part of our lives, more so, I would think, than for most people, than just not having access to your email 24/7. So this is a very intrusive and personalized technology built on this sort of technology designed originally for these factory settings. And so there's a little bit of incongruity there. But this is as far as I could go as far as understanding the limitations of these techniques in taking robots any further until I started my PhD. And when I started that work in Switzerland at EPFL was my first introduction to the field of soft robotics. And this was really the beginning of what I'm going to talk about today and sort of the next steps in my future research interests, utilizing materials to more of their extreme capability. So using compliance in robotics is not a new thing. I would say that the main thing about soft robotics, by the title, is that we're stretching the limits of what kind of compliant materials, soft materials we use in their design. In the prosthetic devices I was designing previously, you can see the bottom plate there of the part that you walk on, the bottom of the foot, is a piece of fiberglass that feels rigid in your hands, but if you put full body weight on that, bends up to a 90-degree angle from end to end. So it's still a compliant element, and it's serving a function in terms it's storing energy and releasing it in sort of a smart way. So we were already doing this to the best of our ability throughout robotics or throughout mechatronics for that matter. But soft robotics takes that next step and goes to materials like silicone rubbers and then smart materials like shape memory alloys and shape memory polymers, which change shape on command to heat and electrical stimulus to do a whole lot more than just act as passive elements of design. So that this work brought me to my postdoctoral work. This soft robotics being soft inherently has a bio-inspired roots to it. Organisms are naturally soft, and so it makes sense to compare soft robotic systems to biological bio-inspired robots. So I continued that on in my postdoc work, and in particular, I became interested in developing actuators themselves to a higher standard or degree of capability than is currently possible with either conventional technology or existing soft robotics technology. And some of this inspiration came from my experience in the dynamic walking community, which is a conference I attend annually that talks a lot about ways that organisms use dynamics of their own body to be more energy efficient, to be more stable or robust to uneven terrains or conditions. And so that aspect is all tied to the type of actuators that we use to drive the systems. And currently the standards we have in the actuators aren't capable of the types of things we're sending them for commands to act a certain speed or to a certain force threshold. The limitations are built into the actuators themselves. So my future work will be along these lines of soft robotics and bio-inspired actuators to improve the capabilities of the systems themselves, starting at the lowest level. So from a little higher perspective, why are these things important? First, I'll say that soft robotics is just the first step of taking robots, like I mentioned before, out of their original applications in fixed factory settings or where they were separated from people by cages, to more personalized applications where they're in direct contact with us, direct interactions, either through through task assistance or through direct assistance, like the type of prosthetic devices that I was designing previously. So this is a view of Baymax, who's a good poster child for this concept from Disney's Big Hero 6. And then furthermore, the types of forms and form factors and capabilities we want, if we want to bring these robots into our world, have to be compatible with our daily living environments. And those environments aren't built to support robots. They don't have perfectly leveled floors. They have stairs, they have obstacles, they have dirty clothes strewn around. So to have systems that operate and function well in these environments, we need to have them, to some extent, reflect our own capabilities and our own limitations. And so you could say that a legged system is very good for this type of dynamic environment navigation, but it has its own limitations, things like instability. It's naturally unstable when you're just in standing. So clearly a wheeled system would do better on its own, but if you add all these other factors in, all these other requirements, it sort of converges on the idea that we should have systems that more closely resemble us. And so here's an example from Westworld where they've perfected this process. But a lot of this comes about through these new materials and definitely new fabrication processes, especially things like 3D printing, which will let this be a lot more accessible to build these systems. And then sort of another direct application of this is if we can design systems that behave a lot like us, why not use the same systems or similar technologies to assist us directly, like the prosthetic devices or like intervention type devices. So you could use robots or robotic wearable systems to augment your strength or to enhance your own capabilities, or probably more realistically, these types of technologies will be used for interactive systems which help us in rehabilitation or gait training, either for learning new skills or more likely just regaining lost functionality through illness or injury. And right now that's the kind of process that's done with a physical therapist or at best a gait training machine which is fixed, but this could be translated into a mobile platform which would become a lot more useful to continue your rehabilitation or your training offline, as it were, out of a lab set environment. And then the last step is these are increasing closeness to our persons, ourselves, is another type of interactive device that might be used for not just enhancing your own capabilities, but maybe extending them. So giving you an extra hand. Dr. Octopus has 4 extra hands. I'm sure we could all imagine how productive we'd be if we had 4 extra hands. Doesn't solve the attention problem, but that's another interesting realistic possibility here in wearable systems, to have systems that complement our functions. So this is that was a view of fantasy, and here's where my talk will start about my past work and how we're working towards these fantasy goals to make them more of a reality. So today I'm going to talk about my work in 3 main areas: modular soft pneumatic architectures that I use to develop my systems, hybrid stiffness robotic structures, which is an approach that combines the best of both worlds between completely rigid robots and completely soft robots. I think neither extreme are the final answer, but it will be something in between. And some of the technical challenges are some of the examples of how I overcame some of those challenges there. And then I'm going to talk about the type of systems that I'm designing for interactivity that typically have this feature of high degree of freedom requirements. So to have a system that is as complex as us implicitly requires that it has a lot of degrees of freedom to be able to manipulate and do things as well as we do. So what are the practical limitations or challenges in that? And it turns out it's something unique for pneumatic systems and soft systems alike. So there's some of my approaches to how I solve some of those problems. And then finally, I'm going to talk about my research in the context of how all this fits into the main mission of Ingenuity Labs and why I think I could be an important part of the community here. So before I talk about modular soft pneumatic systems, talk about soft pneumatic actuator systems in general. I call them SPA systems for short. So here's a really quick overview of my first project, which was just in designing a new type of soft pneumatic actuator. So here's a very basic design of a soft pneumatic actuator, one type of many, which is essentially just an elastic tube, hollow elastic tube with an inextensible fiber wrapped around the outer surface. So that way, when you inflate the the tube from the inside, the fibers constrain the body of the elastic tube to just move in a single direction, in this case, linear extension. And this can be changed by changing the angle of the fibers. So you can switch between having this actuator extend when you inflate it or contract above some threshold angle of how you wrap those fibers. So I use this as the basis of a larger actuator that I called SPA packs. And the paradigm here was combining multiple smaller SPAs to produce a larger actuator, much the way that muscles work by bundling muscle fascicles together to produce higher force output. And this allowed me to generate forces over the threshold of about 100 newtons, which is just an order of magnitude marker to say that this was one of the first high force SPAs above 100 newtons that could be used for applications like this wearable belt. So this is a device I designed for postural support to assist for postural weakness or potentially rehabilitation applications. But what you can't see in this picture here are the parts that I cropped out that became the inspiration for some of my future work. While these new actuators are scalable and let you add all these new functionalities of increasable forces, as well as the modularity of the design in general, that you can place them in these customized locations. The logistical challenges of putting together a system with this many degrees of freedom, as you can see here, are apparent just by the sheer number of tubes it takes to connect these systems to a power or control unit. And so in this case, I bundled them into just 4 discrete groups. But in a better application, you'd want to have some sort of independent control of each of these actuators for this added benefit here, where if you have actuators combined made up of multiple smaller actuators, you get an inherent failsafe from that redundancy that you can only access if you have individual control of every element. And for that, you need to have every one of those tubes connect to an independent solenoid valve. And in industries, pneumatic systems are typically wired to a central console, a pneumatic valve manifold, which is an off-board centralized location of where this control is done. But you can already see the complex challenges that will be involved in that, just in running and routing these cables. So this started from the perspective of this practical challenge of, if we have systems with many degrees of freedom, then we're going to end up with many tubes. How are we going to physically control those things, let alone the challenges that are to come in control from the algorithmic standpoint, which is another long-standing challenge of the field that we will get to once we can put these things together. So my first task was investigating ways that we can assemble these systems with many degrees of freedom in a more methodical way. So that brought me to my first, we'll go back to this, this initial inspiration of Dr. Octopus as a model example to work towards. And in this project, I used this paradigm as the model to design a robotic tentacle, much like I had started in my previous work during my master's degree, but with soft components. And then considering all the challenges there, I came up with this idea to use a centralized power supply. And even before I joined the field of soft robotics, it made sense to me then that to use fluid power would be more efficient than to have actuators distally located in all these independent degrees of freedom. So I took this initial concept sketch from this inspiration and converted this to an actual design that you see here, which is a 3-degree freedom soft actuator module. So there's 2 unique features about this module that I introduced. One is the modularity aspect of it that you can see from the exploded view on the right, which is the inclusion of distribution layers for distributing the pressurized airflow from a central power source, and the embedded control valves that are combined in the actuator as one unit. So every actuator every actuator module contains these actuators at the top in pink, as well as these embedded hardware components used for their control. So what that allows you to do is it saves you the routing of having to move any cables off-board to a centralized sort of manifold valve system. So this became what I have used in terminology before as a type of soft servo. And this is analogous to the use of servos in typical hobby robotics, where it's a standalone off-the-shelf component that you can add to any desired system, but it's really plug and play. So it really only requires a power source, pressurized input to drive the actuators, and a communication line. And then they can all be strung together in series very simply without requiring any low-level design effort to put together a larger scale system. So it saves you some of the complexity of designing something from scratch every single time. And I think this is going to be a future paradigm in the field of people putting together soft systems with off-the-shelf structural components like this. And I said there was a second thing that was unique about this actuator, and that was the actuator itself, which will come up eventually, I hope. This is not a, oops, too soon. This is not the same type of actuator I showed initially, powered by positive pressurized air, but this is powered by vacuum. So this actuator, this video is going. This actuator is powered by vacuum, which means when you pressurize, or rather depressurize, the hollow chamber on the inside, it contracts instead of expands. And this turned out to be very, very useful for a couple of reasons. The use of vacuum in general has a few built-in features, which is that it's power limited because it's powered by the environment. You can never exceed the pressure dictated by the environment that it's used in. And it's also, to some extent, more fail-safe. So if anything were to happen to the actuator itself, like the previous photo I showed of the actuator that had exploded, there was a small hole. There's no significant energy storage in the activation of these. This is a piece of foam, open cell polyurethane foam, which is off-the-shelf material, coated in a thin layer of silicone rubber. So when it compresses, there's no stretching and storage of energy that can be released if anything were to happen, like a puncture. So that's a neat unintended advantage that I wasn't seeking, but really this came out of designing an actuator to be as lightweight as possible to fit that functional requirement of having this extended hyper-redundant manipulator type system. And then it worked out that it works better with vacuum than positive pressure, and to these extra advantages that you get from using vacuum. So I use this concept to build a few different type of actuators that I call V-SPAs, for vacuum-powered SPAs. And I use the spherical rotational degree of freedom one for this module, but I've also developed this type of coiling one and a linear actuator that will show in another project as it comes. So the benefit of creating these modular actuators themselves is that you can create larger structures and robots with a lot more simplicity and ease than it would take to build these all from scratch. And so here's a variety of robots that were built from this single module that can just be chained together. And you'll notice, so for the crawling robot that's shown now, hopefully you can see some videos playing through this connection. It goes from 15 degrees of freedom down to 9 degrees of freedom. Those are all controlled and powered from a single pressurized source at the endpoints of the robot. And that's all it takes, is to connect every module to that shared source. And then they can all tap into the use of the vacuum for their functions. And the use of modularity also gives you this capability of adding different types of modules with relative ease, just the same as you would add another actuator module. You can add suction cup modules for manipulation and for adhesion, for sort of climbing applications. And then another very important, to me, something that was really unique about adding the vacuum is you can use vacuum-powered variable stiffness mechanisms to change the structural stiffness of the system. And for a soft system, that's very important because inherently systems that are soft can't necessarily bear the loads that they might be tasked to use or to interact with in object manipulation tasks, for instance, or just to support weight. So it's really important to be able to change the stiffness to accommodate those higher loads. And this picture on the bottom right is an example of one module I developed based on vacuum jamming, using vacuum to basically compress particles in a sealed bag that become stiff when they've been activated by vacuum. So that lets you selectively choose between soft and stiff states. And that turns out to be a very useful attribute for soft robots. And traditionally, this was done with independent power supplies. And the ability to use vacuum for actuation means that you can have a single vacuum-powered robotic system with no other peripheral systems for power. So that's another great feature. As I said, having this stiffness element as part of the robot is necessary at times. And in some cases, you don't necessarily need the selectivity of it if it can be designed into the structure itself, if you always know where the stiffnesses need to come into play. For instance, if you have just a single degree of freedom that you need compliance in, like in a finger joint or something, or an arm, you need the rest of the degrees of freedom to be relatively stiff, so you could bear loads out of plane of the actuation, perhaps. So going back to our inspiration of Dr. Octopus, I decided to take it a step further, whereas before I had removed the element of human interaction and the wearability component, I started to consider this as one of the design requirements for a new module, which was updated to take into consideration these ideas, elements of adding stiffness components to the soft robots. So maintaining soft actuation, but still having the degrees of freedom constrained in an intelligent way to be able to support loads to assist in tasks. And so these are just some sketch ideas of ways you could use a type of wearable system, not for the mayhem that Dr. Octopus uses his for, but for just relatively ordinary daily tasks where it'd be useful to have a third hand, or a replacement hand, perhaps, if you've lost functionality, a wearable system that could. This drove some of the design requirements for an updated module that I'm showing here. You can see is still, well, it has the same degrees of freedom as the original soft vacuum-powered module that I showed earlier. But in this case, I've changed the use of vacuum-powered actuators to this other type of low-profile pouch SPA. And one of the reasons for that, you could take this structure, which is a kinematic structure that's origami-inspired, which means it's built mostly of flat or rigid plates that are separated by a living hinge, flexible joints, to give it sort of defined degrees of freedom. You could take the same structure and place that over the previous module that I had. But if you could remove that actuator and provide it in a different way, the way I've eventually done it with pouch SPAs, you get this added benefit of having a fully contractible actuator. And so having a body of an actuator stuck inside of this structure would remove that possibility. But using this other type of actuator, I can actually contract these actuators to a completely flat, folded, compact state. And that's something I thought could be useful for realistic wearable application where you would want some sort of stowage capacity. So to be able to deploy and then store a system that you're carrying around with you for when it's needed only, and then put it away when you don't. So the thing to note about this structure is it reduces, has no degree of freedom in torsion. And so that was the main reason of creating this type of structure. The actuators in the three actuator module I had developed before could only support loads, even loads that were relatively heavy. It could lift against those loads, but any force out of the direction of those actuated degrees of freedom, it couldn't do anything about, save being able to just stiffen when there was a load in that degree of freedom. You would then lose the range of motion to move at all if you were to just completely lock the actuator in place. So this structure allows degrees of freedom in all the two dimensions of sort of X and Y motion of that upper platform relative to the lower one, but reduces the torsional degree of freedom entirely, which is all taken up by this foldable structure. And so these are the initial prototypes of getting the joints to work, and you can see how the pouch SPAs actuate along the edge of the hinge. So the structure itself becomes an active element of the actuating component of the module. And so here's a view of what the final actual system looked like in operation. This was actually created by a form of layer fabrication. It's a technique that I used in the production of the other soft modules, the soft servos, to create the distributed pneumatic channels in the bottom layers. And you can see in the ray exploded view that I did the same thing here. So this is produced out of layers of glass fiber composite, multiple layers of this with thinner flexible layers in between, sandwiched between these rigid upper and lower layers that spans that span gaps between rigid plates that are independent rigid bodies. And so those show up as just dark orange spaces in between the plates. That's the flexible material that's underneath the top and bottom rigid plates. And it was all fabricated in a single step. So everything you see on the right that is the same color was more or less a single piece at one time, with the edges trimmed away to allow the degree of freedom. So that really, the functionality really is complemented by this ability to manufacture them in this unique way, and vice versa. So being able to manufacture these things is one of the inspirations for the design in the first place. And so if you want to produce multiples of these, or to have these embedded features, it's nice to be able to do those in the single step of, or two-dimensional manufacturing, which is readily available through things like CNC laser cutters. So this is produced on a laser cutter and then heat pressed together in a laboratory press machine. And it has all the same functions of the other module, containing a solenoid valve on board, and the electronics printed circuit board built into the module itself, so that these modules can be chained together in stacks, in a serial stack, and powered off of a single power supply, a single positive pressure power supply in this case. And so this is designed to be able to support heavy loads. As I mentioned before, it removes the degree of freedom and torsion, but conceptually, because it's powered by positive pressure, you can increase the capacity of this actuator module by increasing the pressure. And the only limitation there is driven by the manufacturing process and the materials that you use for the actuators themselves, and other things like the joints, which are also bearing the loads that it's trying to restrict. But this is a materials science or materials engineering problem solved, not a conceptual one. So as a design, this is much better suited towards these higher force applications, which can be improved by investigating new types of materials to fabricate them, but using the same sort of straightforward process. And then the last example I wanted to show is this type of ways that you can use high degrees of freedom for an interactive system, not just in building systems that sort of replicate our functionality or complement our functionality. If you're thinking about sort of humanoid, bipedal, or bio-inspired legged robotic systems, which is an interest of mine. But there's other types of high degree of freedom systems for interaction where you can take advantage of this, the high degree of freedom to render high fidelity control or feedback for different purposes. So these are some existing examples or previous examples, not my work, but you can see there's very actually limited other examples of this type of work, but it was motivated initially, I think one of the earlier projects were these haptic devices, which is the second one from the left, of a pixelated surface, a physical pixelated surface that could change its contour by changing the height of each one of the pixels to create a two-dimensional surface structure. And then MIT built this other one on the very far left, the Inform system, a little more recently, to demonstrate the same functionality as a haptic device, but for larger scale demonstrations of human and computer interactions, to physically render spaces that you would normally do in virtual reality, but on a tabletop surface. And then there's only a few examples of soft systems that sort of replicate the same functionality on the right. And these were the state of the art up to maybe 12 degrees of freedom of individual pixels on the upper right example there. But one of the reasons I think that there are fewer examples could be that, as you can see on the MIT's Inform on the left, there are many, many degrees of freedom and a lot of overhead that it takes to drive these individual actuators. So those are all done with mechanical motors, linear motors, and cable transmissions up to rigid sliding pixels that move up and down. And it takes up about the size of a small dishwashing machine, I would say, or a washing machine. So just to get that functionality on the surface, there's a lot of overhead production underneath. But modular soft pneumatic systems are very well suited to solving some of these challenges. I'm good playing too. And you can see from this that there's two very interesting applications you can use this for. One is basic object manipulation. So you can use this planar surface that changes its contour to drive objects across the surface. And Festo, one of the examples I showed before, is looking to a system very similar to this on a larger scale for industrial operations, in moving delicate components and to roll them around on the surface. So it already has, in the time of me first looking at this, developing this system, taken steps towards practical real-world applications, sort of in industrial spaces. But then another interesting thing you can do with this type of system is provide a more high-fidelity haptic feedback than you normally get from vibrotactile outputs that we typically use in haptics. So what's normally done is that we have maybe an array of sensor or array of small actuators, haptic actuators, which can buzz at different frequencies or different intensities at best to change the amount of information that it's conveying. But it's really limited in a certain sense, limiting in how much you can convey through just those modalities and placement of sensors, number of sensors, or the different modes of actuation. So this lets you, this type of surface or type of display, let's say physical soft display, lets you render physical patterns or physical shapes in any number of ways. And so it really expands the level of feedback that you can apply in a sort of human robotic interactive system. And I think there's other even more practical applications of this beyond just providing haptic feedback, which in itself is a very interesting topic. The same type of system could be expanded into a larger, you could imagine a bed that you lay on, a larger type system. And this came to me as a possible application when I learned about some of the problems in patients who are bedridden, who are limited in mobility, that they have to reside most of their life in a bed, in a hospital, under supervised care for long term. And so if you're in a bed for that long, you have to be manually maneuvered or moved and repositioned to prevent the formation of bed sores. And so that happens anywhere you have a bony protrusion pushing on, generating high spots of pressure between you and the surface you're lying on, which can cause damage and injuries to your skin or the muscle between the bed and the bone. So this type of system could be used to directly address those points of high pressure and reduce the pressure to reduce the incidence of bed sore injury. So this is one of the applications that I added a module for sensing on top of the same reconfigurable surface. So what this did was add it's a flexible sensor, not a soft sensor, on top of each one of these individual actuators. So these actuators move only up and down, but in the event of a bony protrusion, you would get a high interface pressure read by the sensor, which is shown as a red pixel or a red dot. And then when you read a higher force or higher force at that point, you can retract the sensor to a certain specified threshold of force to sort of alleviate and redistribute the force. And so the right hand figure shows what the system looks like before, when it's off and on. And these are a cartoon map of what it would look like from above in a 4x4 grid when you have only one protrusion. And then when you turn the system on, it redistributes that force to a larger area, reducing the incidence of the interface pressure at that point. And on the bottom left side, underneath the actual photo, those are real photos. That's real data that was taken from an experiment that I ran, where in this case I had the protrusion only around the outer perimeter of the device. And you can see that when the device is off versus on, it was able to reduce the interface pressure on the surface. So something like this would be very critical in a real sort of bed sore application. So that's all I have for the examples of my past work. Sorry, talking really fast, but there's a lot to cover here. So this type of work, it's a big delay. Sorry. This work is a rough overview of the type of work that I'm going to be doing in my lab here at Queens. I call it the Novel Engineering and Robotic Devices Lab, or NERD Lab. And it has three primary objectives in my research. One is to further develop more bio-inspired actuators to address the deficiencies in existing actuation, to give us machines and devices that can perform in ways that we can't achieve either because of scalability or because of force and dynamics capabilities. The ability to be backtrackable is one very important aspect of dynamic walking robots, for instance. And it's something that I'm very interested in looking at to develop more agile systems. Materials and fabrication is intrinsic to everything that I do. As I said at the very beginning, a lot of these designs are driven by the material properties or the requirements sort of dictate that new materials need to be leveraged for some of their advantages. Morphological computation is a really fancy term that people like to use in the field of soft robotics, but it means that the computation that you normally use in actual computation can be offloaded to the materials themselves. And so you save how much control you need to apply just by using a softer gripper, for instance. So if you use a soft gripper that automatically conforms to an object, then it saves you a lot of the difficulty in having to program each degree of freedom or joint function in a manipulating hand. So that requires these new materials, or at least the use of passive compliance in the design. And then these together are going to be used to develop more capable systems and devices, doing things that you couldn't normally do if you limited to these off-the-shelf hardware components. So when it decides to change, how is my lab going to fit into the rest of the Ingenuity Labs community? One advantage of being around for a while is I get a chance to meet everybody and see a lot of the work that's been going on. And so here's how my lab fits into the three main themes of Ingenuity Labs, and how I think some of my work now and into the future will fit into each one of these themes. So soft actuation from the start is an obvious first place to contribute. The direct applications of this are built into this theme of assistive devices and human sensing. So these are things that I've already explored and plan to explore further, directly working on assistive devices that interact with us, that either extend our capabilities or can be used in rehabilitative applications. And I have everyone's name that will come up, so not everybody is on the same list, but it's because everybody can sort of span multiple areas. But Jingwo Li is one person I could work with on these types of assistive devices, and soft actuators and sensors, which serve those purposes. And then extending some of the work I've done in haptics already, working with Kayvon and Ingenuity Labs would give me an opportunity to find ways to use these devices in experiments or to develop them further into new form factors. I'd be very interested in that. And then my interest in building augmenting systems for rehabilitation or training, Nick and Paul from Ingenuity Labs are also working in sort of a similar space of augmented realities using for human and machine interactions. And I think bringing the physical space into those problems would be very interesting. So there's a lot that can be done in augmenting human-machine interaction just in the virtual space. But I think extending that to physical space has always been one of my aims, particularly for some of these wearable soft devices which aren't strong enough to support high loads that you would normally build a conventional system for. One of the limitations of the soft actuators is they aren't inherently as strong, but that's not necessarily, sometimes a bug is a feature. In this case, you can still use the same system to provide informational feedback. And I'm particularly interested in this type of implicit feedback where you don't notice you're being coerced into one motion or sort of training exercise. You don't really notice what you're doing, and that's sort of the role that the physical therapist plays, is not replacing your function or supporting your own limb movement, but just giving you an idea of how you should move. And so I think those, working with some people in Ingenuity Labs would give me an opportunity to actually go after some of these applications. Let's go forward, not backwards. Second is the smart environments and infrastructure section. I think my work naturally fits into this because these are some projects that I've already had in mind for a while, which are amenable to this strategy of modular design, as well as scalable design. So some of the advantages of layer manufacturing, for instance, are that they're inherently scalable. And I'm very interested in building things at what I call the meso scale. So not quite micro scale and not the larger scale that we find most robotic systems built in now. But at this small scale, centimeter scale, robots can be used for a lot of things, in swarms in particular. So I'd be interested in using these types of systems for not throwaway applications per se, but applications where you don't suffer much if you lose a system, or you don't lose much of your functionality if one of many systems goes out of function. Applications like bridge inspection or underwater asset inspection are two things that I've been interested in working more in the future. And I have some other projects I couldn't show today, but underwater robots that are scalable to the small dimension that could be used for monitoring or exploration or sensing in remote environments. And then for actual applications, what smart environments and infrastructure means to me is having devices that have physical intelligence built into them. So the interface pressure adjusting modulating bed is one example. You could take the same concept and imagine that your chair adjusts to your posture. Maybe it could give you feedback and say, sit up a little bit more. Or it could change its shape to provide the physical support without you having to think or move in a way that's more biomechanically favorable to prevent injuries or back pains. So there's a lot of ways you could use these multi-degree freedom systems as embedded functions in your existing, in your home, for instance, or even a backpack that adjusts its contour on the back. I don't know. But these are ideas I'd be very interested in exploring with some of these other researchers at Ingenuity Labs, especially in the bridge inspection and some of these outdoor infrastructure inspection things with Neil and Josh and Ali as well. And then finally, the intelligent mobile systems is an easy one for me to say that I fit into. A lot of my work was motivated by my participation in these conference events like Dynamic Walking, where I was introduced to bio-inspired robots in the first place, the advantages of their final intended use, and then the disadvantages in how we currently build them. And these are challenges that I want to be a part of addressing myself directly. So as I mentioned before, swarm robots are a very important, a very useful potential application for this scalable technology that I can imagine working with researchers in Ingenuity Labs like Sydney and Josh and Amy, who are also very good in controls. And so it's going to add, developing new hardware is only going to introduce new problems, maybe in the software and control side of things. And I think it's important to be an inclusive part of a community that has solutions to all of these independent problems. And then lastly, on top of all these things, Ingenuity Labs having a specialty in artificial intelligence and machine learning is going to be critical. So one of the next big steps or big challenges in the field of soft robotics or anything has to do with compliant systems is dealing with the dynamics and dealing with the number of degrees of freedom. That if we try to just model these systems, it may be more work than it's worth if we have other solutions like learning algorithms, which can implicitly derive these input-output relationships. So for controlling soft systems with infinite degrees of freedom, you might say that there's only one way to really do that well, and that would be through some sort of a learning approach. So that's not my area of specialty, but it's definitely something that I'm going to need to incorporate in the future if I want these systems to be fieldable. And a lot of my focus is in making these practical, useful systems. So there's no point in that if we don't know how to actually utilize these. And then the very last point is that these are a few highlighted patent ideas that I have either on the table or in works for using some of these devices. My interest is not in commercializing and making a lot of money off of these, but I really want to see these devices and this technology in the real world making a difference, because that's where I think it really stands out.